This is a video run through on the CFX tutorial 1, the static mixer tutorial. Basic outline is this is the geometry you'll be modeling. You have two inlets, one on each side. One will have hot water passing through it, the other have cold, and you're looking at the pattern of flow as they mix here and flow out through an outlet here, hopefully at a uniform temperature. So the dimensions, there's a document called Mixer Specs. So if we open up new Solidworks file, new part. Solidworks is standard across most engineering industries and is an invaluable skill to have. If you haven't already had some experience with SolidWorks, then this will look particularly valuable on your CV when you're applying for jobs across all areas of engineering. So it is very useful to know. And it's geometry modeling. I'm just going to work through this and hopefully I'll pick up a few ideas about how to use it if you haven't seen it before. First, we have to draw our cross-section, essentially cross-section through our geometry in 2 dimensions. And we have to, in order to draw in 2 dimensions, you need a plane to draw on. So we choose over here on the left, the features box, we choose front plane. And there we go, click on that. And we also choose sketch then after that. We want to look at it flat on, so if we click on the Z-axis there, it'll flatten it out for us. First thing we want to do is draw the center line of our mixer. So start off here, and when we go into the page, it shows us the origin here, 0.00. And if we draw a vertical line down from there, if you just draw it down, it'll keep it vertical. So we have a line there. So the center line of the so click on this here. Click on the you press escape, it'll just terminate the current command. It was trying to draw another line there. So when you press escape, it just completes the line. And so a very useful thing is to use the smart dimensions up here on the top left. So when you dimension an object, so just click on it there. So that's 40.97 long. We actually want it to be 4,000 long. And all we do is put in 4,000 there. Put it in millimeters if you like. And it will just scale it to that. And so now we can click this here. There are views here. Click this guy here to zoom to fit. And next, we want to complete the profile. This, so we do this as given in that document there, similar to the mixer specs document. So we start our line again, and draw a line out of here. So ultimately we want to be 2,000 long. Doesn't have to be there. We can put a dimension on it and change it in a minute. So something close to 2,000. And we want to come down here, 2,000 as well. There we go. And I'm going to come across to about within 500 of here. That's about there, and then down about 1,000. And I think that's and if we come down to here, these guidelines will appear as you're using it, so you can be sure that you're level with the point you're looking at. Okay. So if we dimension all the relevant sides here, this one here, and it should be 1,000 in fact. Dimension this should be 1,000 as well. When you put in the smart dimension, 2,000 in fact, change that down here on the left. Okay, that looks a bit more like it. And put in this here, 506.8, we just put in 500 here. Okay, that is what we call the profile of our rotated surface. In order to convert this into what's called an entity, we compress this guy here, and it will, we can now use it. Press the green tick over there, and it's completed sketch at this stage. So we take sketch 1, we make a revolve boss base out of that, and we want to revolve it through 360 degrees. Really the only input here we have to provide is our axis of revolution, which is this line here. And that will give us our three-dimensional shape there. And press a tick to give us our solid. That's the main body of the mixer. Go back to that 2D view now. Proceed with the, go back to sketch. Next thing we're going to do is draw a cross-section of the pipe in around the center of this part here. So we're still working on the front plane. And we select circle with center up here. We have a number of options. We want circle. And if we bring it in somewhere in the middle of the section here, and make sure we've selected front plane as our drawing plane. And draw a circle any size. We can set the specifications of it down here. So these specs are position of the center in X and Y on the plane, and also the radius. So we want the center to be at minus 1,000 millimeters. So we put in minus 1,000 there. We want the radius to be 500 millimeters. And we just put that in, and we have it. It will adjust to the size. So that's the first one finished. We go back to features now. We can press this to be press this to complete the sketch. Go back to features, and it's called sketch 3. Anytime you make a mistake or do a dud sketch, it'll still record that number. It'll use up the number. That's why it's called sketch 3. Nothing to panic about. And this is going to be an extruded boss. So this extrudes it just in a straight direction. So it takes that circular cross section, and we're going to extrude that through a distance of 3,000 millimeters. And this is a useful control here. Let's reverse the direction of the extrusion. We'll use that in the next one. And I think that's all we need for this. See there, if we go along the top menu here, you can see this here view is view orientation near the middle. And we can select an isometric view there. And it looks like we have our pipe there. So we go back to the frontal view and go back. I'm going to draw another circle in here in the mirror position to the first one. So we go back to sketch, and we select our front plane as our drawing plane, and we select circle. So I'm going to draw a circle in approximately the position, just so we know what we're in around the right position. That's it there, and we reset the dimensions here to 1,000 millimeters in the X and minus 1,000 in the Y box. The radius is a little bit large, it should be 500. And when we click that, we have a mirror image of the original one. And we complete that by clicking this. Go back to features and sketch 4 there, and we want to extrude that. Make an extruded base out of that. We have our this maintain the distance from the first one, but we need to press this reverse direction as we want it going out in the opposite direction, the negative Z direction. So we've selected that. And then if we look at that in 3D again, we have the geometry we're looking for there. We have our central vessel with 2 side pipes coming out of it and an outlet pipe there. Okay, there's one bit extra you need to do here, and that is to save this as an IG's solid model. So if you go to File, Save As, and let's call it Static Mixer. Select IGs from Save As type. And choose your directory. Save it somewhere on your Z directory preferably. And save. In order to do the computational fluid dynamics part of this now, you need to go to simscale.com in a browser, preferably Chrome. Open simscale.com. So, if this is your first time, you'll probably be given the option to start an account. I've already got an account, so I'm just going to click on Start Simulating now. And I'm going to click New Project when you get to the dashboard. That doesn't come up automatically. Click on Dashboard and click New Project. I ask you for some information on your project, what you're going to be doing. It's going to be called Static Mixer. And what we're modeling is heat transfer in a static mixer vessel. The reason they need to put in a description, just a bit of detail about it, is that all of these projects, the software is free. All of the projects can be are on a public database, so other people can look through them. So it's good to give an idea of how much or what's happening here. So we create the project after putting in our little description. And so we want our file. So we can import from the computer. So wherever you've saved your Solidworks file, and actually saved it as an IGs, but you can also input Solidworks object as well. Let's import that. Click on Import there. Might take a minute or two. A lot of data to take in. So this is just taking in the geometry now into SimScale. So when it gives you the option, click on Create Simulation. We have to specify some settings here. A lot of different things. You can simplify it by just say incompressible. It's the simplest type of analysis. It's just flow. There's no heat transfer or anything like that. But our problem will involve heat transfer. So best one that we can click on for our needs is convective heat transfer.
So we're simulating heat transfer in a fluid by either natural convection or forced convection when the fluid motion is induced by external forces such as inlets, pumps, or fans. This analysis type also allows to model heat transfer via radiation. This will do our purposes, so I'll click on Create Simulation. Some more, so we've selected convective heat transfer. We need to specify our turbulence model. Leave that as the default K omega SST. This is the most stable one that I've found. Leave time dependency at steady state. Later on, we're going to look at transient, where it's changing with time. We're going to stick with steady state for the time being. Radiation, leave that off. I'm going to keep it as simple as possible. We're looking at convection heat transfer. Radiation isn't going to be a significant part of it within a fluid. And passive species, leave that. So click on that tick there. We're ready to go. So we have our geometry there. If you left click on the background and hold and drag, you can rotate the shape around. So if we look at our click on, we're going to go down through this menu here. First thing I click on here is model. It's looking to specify gravity. And so if we look at our axis down at the bottom here, so gravity up down, it's going to be in the y direction, and it's going to be downward, so it's in the negative y direction. We're going to specify gravity at minus 9.81 meters per second squared, and 0 in the other direction. So next thing we need to specify is our material, but in particular our fluid. So click on material and go down through the list. Default is air, but we're going to be looking at water. Gives you a set of default conditions there. Density 997.3 in about 1,000. Thermal viscosity particularly important. Kinematic viscosity, specific heat 4180 joules per kilogram per Kelvin. So the standard properties, we apply that. And so this is our properties as applied to this volume, DE33, this guy here. Click on the tick there to accept that. We can skip to boundary conditions now, and this is where we really define the problem. So first of all, if we click on, we go back to this diagram here. What we need to specify is that we have a flow in here of 2 meters per second at a temperature of 315 K, and in the other pipe, 2 meters per second, 285 K. Then we also need to specify an outlet that it leaves through this bottom pipe here. That's all we need to specify then. So in order to do that, we have to specify the velocity. So we create what's called a velocity inlet. And so if we click on in this phase here, and it gives us the name of it there, not too important, but as long as we have the location correct. And we want fluid going in perpendicular to this face. So that would be in the Z direction down here. So that's the Z direction. It'll also be in the minus Z direction because you're going from Z to X towards the origin. So we would put in UZ of minus 2 meters per second. And if I click on that, we also need to specify the temperature. Bring back up my diagram here. It's 315 K. So we need to specify all the necessary information on the inlet. And say it's 315. Default is C. We're going to change that to K there. That's what we have. Now, if I make sure to click on the tick there, we have our velocity there, our temperature, and our location. I'm going to create another one then over here. So click on the background and drag. I can rotate around. Give me the Let me see this face here. Click plus here, it'll create a new one. Select velocity inlet. Select my face. Now, go along this direction, which is the positive Z direction. So I change this to 0.0 meters per second, UZ. And I need to specify my velocity, which from the previous diagram was 285 Kelvin. And select that. The other thing I need to specify then is that fluid is free to flow out through this bottom face here. So now I'm going to specify what's called a pressure outlet. Well, first of all, I select the face. That's where it's going to be. It's called a pressure outlet. I specify then the pressure on this face. I'm going to specify the gauge pressure as 0 pascals. Gauge pressure is pressure relative to atmospheric pressure. It defaults atmospheric pressure to 101,350 pascals, 1 atmosphere. So we just specify 0 pascals. I'll set the pressure everywhere here to 0 pascal gauge, or atmospheric. We're assuming it's open to the atmosphere now. And then click the tick, and we have our. I can click through our 3 boundary conditions in. And so that's the bare minimum what we need to set for the fluid. We set the type of fluid, set the velocity and the pressure on the boundaries, and the temperatures. Then what the software is going to do, it's going to solve for every quantity, velocity, temperature, and pressure inside the static mixer then, and also solve. And we'll be able to get the velocity and the temperature of the fluid coming out. If we have a look at mesh then, it defaults to a mesh, what's called a mesh fineness. So that's how small the mesh elements are, hence how many of them it will take to fill up this volume here. Defaults to 5, an average value. I'll make that a little bit less. Let's put it in here. Let's try 3. And so if there's less element in it, it will run quicker. This is an introduction, so we wanted to run fairly quickly to see that everything's working correctly. So if I click that and generate, that'll actually take about a minute to 2 minutes, depending. And so I just leave it to run there, and have a progress bar at the bottom there. Now it's finished there. So you can see it's broken down that volume then into these tetrahedral, triangular, smaller volumes. It's going to solve for the velocity and pressure and temperature and so on within all these. By default, if you don't set a boundary condition on the surface, so all the other ones that we haven't set it on, set out the inlets and this outlet here, it assumes that they're walled solid. We look at up close at this one here. What it also does is next to walls where there are going to be boundary layers, creates this layered effect pattern to capture the boundary layers, the variation in the velocity across the boundary layer. This is quite thick. If we're looking for really accurate results, then we'd have to make that finer. We'd have to increase the mesh fineness much more. What we want is to run quickly, so we're going to leave it at 3. That's our mesh generated. So click on next, go down to the bottom, simulation runs, and click the plus to create a simulation run. Estimate is that it's going to take 0 to 11 minutes. If I click start run, and it'll start preparing the simulation. It's a matter of waiting now, really, for a few minutes. And after about a minute, you'll see the progress bar building up there. And if you go on the left here in the menu, expand out settings here. And down at the bottom here, you'll see convergence plots. And click on residuals. So the residuals are a measure of the level of error in the calculation. As long as this is dropping, you know your solution is getting more and more accurate. Probably we'll discuss this a bit later in class and look at how residuals correspond to the accuracy of the solution. Basically, this is still dropping then. You're getting more and more accurate. And this is going to run till about 1,000 iterations. This probably already has. It runs fairly quickly because we have a coarse mesh, not that fine. It says it has run 100%. It's great. It's just tidying up now. It's going to produce results in a couple of minutes. So after approximately another minute, this will say finished here. We can click on post-process results. We can look at our results. If first of all everything's set up as we want, and then what kind of answers we're going to get. Easiest way to visualize things is what's called a cutting plane. That's cutting plane down through your volume. This top one here, parts color, is the actual 3D volume itself. I'm actually going to make that invisible by clicking this toggle here. So you see there we're having a plane down through down vertically through the mixing vessel, the Z plane, down through the middle. You can see that as you go down more and more, food is mixing, and it's getting progressively, hopefully mixing up, and the temperature is getting more uniform. So possibly a better view would be a Y plane. If we rotate that around, click on left here, it'll just give you the vertical view on it. And you can vary the position of the plane by clicking the slider bar. This is moving it up, I think. Now we see the pipes as well. So what we're seeing here is the velocity, in fact, not the temperature. So I want to see what the temperature looks like to see how the fluid is mixing. And we have cold coming in here, hot coming in here. We have kind of an average in the middle there, but still very much hot and cold areas. Let's try running that down through. So going down, you can see it's all more uniform temperature as you go down towards the bottom. And we'll go back up again. I want to check what happening with the velocity as well. You see on this menu over on the left here, the vectors. You can turn vectors where it represents the velocity by little arrows. And I'm going to zoom in on this. You can see the arrows at the inlet there. You have uniform velocity, and that should be 2 meters per second coming in there, in here, and then they spin around each other and they mix up around here. And so you get a rotational flow, so zero rotation in the middle, so getting very little velocity in the middle. And if we look, then we bring the cutting plane all the way down to the bottom. So that's as low it'll go. We're seeing a uniform velocity. And let's see what the temperature, and let's see what the velocity is like. Click on velocity, the velocity magnitude, some of the components. Fairly uniform. It's high speed area there, lower speed area there, but colored according to the velocity. And let's see what we can also. It'll also print out all the statistics for that plane. Then, cutting plane 1, average velocity is 4.18 meters per second. Now you have 2 points with 2 meters per second and 2 meters per second. Average is about nearly at 4 meters per second. Some slight error there possibly, but that would be remedied by making the grid finer, putting in more cells. So let's look at the same for temperature then. What's our average temperature? Average temperature is 300K. So it's the exact average of 285 and 315. So that's as expected. Okay, that's our first simulation. I will look at some more of the results. And rotate that around there, change it to a Z plane. You can see the areas of our cold and our hot inlet there, and it's flowing out the bottom as well. And so that's our first simulation done, and we'll move on after this.